Hi, everybody. Welcome to the February 2025 SJAA imaging meeting. And tonight we have Julien, who's going to show us how to do spectroscopy. Julien, take it.
皆さん、こんばんは。はじめまして、Julien to moshimasu. Nihongo wa amari hanasemasen. So since my Japanese is relatively limited, I hope you won't mind if I continue the presentation in English, which my wife also claims is very much a work in progress. But anyway, I'll do what I can. So first of all, thank you very much for having me. It's always a great honor to talk in front of the SJ Imaging SIG. And if you would like to present, he is always in search of new speakers, so please reach out to him. Tonight, we're going to talk about amateur spectroscopy and more specifically about nighttime spectroscopy. So I'm going to go ahead and share my screen now. And there's the slideshow. You can see my slide? Okay, I assume you can see my slide. All right, so this is how I structured the presentation. So I'll do a quick intro, talk about myself a little bit of shameless promotion. I'll talk about the equipment. Please hold off. If you have any questions, please hold off during this section. And then we'll move on to live acquisition of spectra on nighttime targets. During that time, I encourage you to unmute your microphone and ask as many questions as you would like, because we'll do short exposures. And so while we're acquiring the data, it's kind of like watching paint dry, so you can ask questions. And then we'll try and process the data that we acquire together. And then I'll cover why I think amateur spectroscopy is such an amazing area to venture into. And then we'll do a quick Q&A at the end. All right. So a little bit about myself. So my name is Julien. And some of you know me from SJAA or TAC. You may also know me from my YouTube channel. If you're not yet a subscriber, now is the time to hit that subscribe button. And I talk about a variety of topics on my YouTube channel, including spectroscopy. Let me talk a little bit about the equipment we're going to use tonight. So this is my telescope. This is the ASCAR 151 PHQ. So that's a 6-inch refractor, a quadruplet Petzval refractor. A very, very nice refractor. I actually reviewed it on my YouTube channel almost 2 years ago. And I'm very happy with this telescope. It is mounted on an Ioptron CM70. And that mount rests on the Ioptron tri-pier. So this is the mount, and you can see there's a little custom counterweight here. This is the spectrograph that we're going to be using tonight. So this spectrograph is called StarX. It started as an open source project where you could just download the STL files and print it yourself. And then you would order an optical kit from a company called Cheliac Instruments in France. And you would be able to assemble your spectrograph relatively easily, all by yourself, and get amazing results. So this is the StarX version. There is a corresponding spectroheliograph version called SolX, which also allows you to get amazing images of the sun. I'll share a few things later. So where was I going with that? Right, so this specific version is a little bit different. It's an enhanced version, which was designed and is manufactured by a company called Azure 3D Print in France. So I actually reviewed this kit on my YouTube channel last October, I think. And you can still purchase it today using the discount code that I share in that video. And it's an amazing way to get into spectroscopy. It's relatively inexpensive. The 3D printed kit and the optical kit together, it's less than $1,000. And you get something that is extremely powerful. I have another, I'm going to stop sharing for just a minute so you can see my screen. Let me go back here so you can see me. I have a second star X here. You can see in my hand. Oops, right here. So why do I have two spectrographs? The one that we're going to use tonight that's attached to my telescope is configured in high resolution. So we are going to zoom in around the H-alpha line. And we'll have a spectral range of only about 20 nanometers. This one is configured to work in low resolution. And so I can use it over the entire visible spectrum from 400 nanometers to 700 nanometers. And I can also, with a few small changes, by changing the grading, which is underneath this wheel, and by inserting a filter, I designed and 3D printed a little filter holder here. And you can insert a rejection filter. You can actually use this to do near-infrared spectroscopy. I have a camera, which is the ASI 715MC. It's a color camera with a tiny sensor, very good for planetary imaging. And that camera has the interesting characteristic of being very sensitive in the near infrared, to the point where beyond 800 nanometers, the Bayer matrix is pretty much transparent. So I actually haven't tried it yet, but I would like to do near infrared spectroscopy with this second spectrograph that I have and see what we can get with that. All right, let me share my screen again. All right. So here's how the spectrograph works. This is how the starlight comes from the telescope. It hits a slit, which actually is not 10 microns. Mine is 15 microns. And the telescope focal plane has to be placed exactly where the slit is. And then you have a collimating lens, which turns this beam of light into a parallel rays of light, and then it hits the grating. And in my case, the grating has 2,400 lines per millimeter. And then there's an objective lens. And finally, the spectrum hits the imaging camera sensor. So this is an image of what the slit looks like. It's actually a mirror. And there's a tiny line here. I don't know if you can see it. There's another one here. This is actually a multi-slit. There are 4 of them with different width. So the one we're going to use tonight is 15 microns. And here the assembled spectrograph attached to my telescope. The science camera we're going to use tonight, which is here, is the ZW-ASI 533mm Pro. And the guide camera here is the ZW-ASI 220 mm Mini. Okay. We're also going to use an electronic finder scope, which is the Skywatcher EvoGuide 50ED. By the way, amazing unit. I used to use those cheap guide scopes that use an achromatic lens, and I always got really bad results with those. The Skywatcher EvoGuide 50ED is really good. It's a little bit more expensive, but it produces very good images and pinpoint stars. So highly recommended. I mounted it to the handle of my telescope using a custom designed 3D printed bracket here. And we're going to use the ASI 120mm camera here. We're also going to use a mini PC and a Pegasus Astro power box for power distribution, dew heater control, and so on. And finally, we need a spectral calibrator. Just a sec. So this is the spectral calibrator that I used to use. That's not the one we're going to use tonight, but I didn't have a good photo of the new one. I do have a video I'll show you in a sec. But basically, the spectral calibrator, what it does is it allows you to inject monochromatic light into the spectrograph. And that monochromatic light is going to give you lines that are at very well-known wavelengths, and that will allow us to calibrate our spectra. So I designed and 3D printed the Rolls-Royce of spectral calibrators, and it looks like this. It's also a telescope cover. So I have a quick demo. Let me show you if it works. This is a cover, pretty straightforward. It is controlled via SRAM. There are little magnets that hold the cover in place when it's either open. Whoops, sorry. Either open or closed. Let me see if I can play again. I don't know if I can stop. I can't stop the video. Okay, that's fine. All right. But then on the inside of the cover, there are 4 little slots, as you'll see in a second. And those are not LEDs. They are neon bulbs. Okay, so they require 100 volts to turn on, and all of this stuff you can actually look at it, how I designed it, how I built it. I actually have it right here, and let me blow this up a little bit. So this is an open source project, and I show the finished product, the demo that you just saw, all of the hardware, the schematics. You can even have the PCB 3D printed, or not 3D printed, but printed by a company called PCBWay, for example. And then you solder your components. And then there's a 3D model that scales relatively well. And this is how to wire it. Okay. And then it is ASCOM compatible, so you can control it via Nina. And I'll show you how it works tonight. So that's what we'll be using. Let's see, what else do I want to talk about? In terms of software tonight, what we'll be using is we'll be using Nina, PhD2, Carte du Ciel, and SpecInti. And I'll show you guys how all this works. So I'm on a Mac, but I'm going to connect to my mini PC using Windows Remote Desktop. Hopefully it works. All right. Cool. So I have 2 instances of Nina running here. This one controls the mount and the camera attached to the electronic finder scope. And the other instance of Nina controls the science camera, the focuser, and the spectral calibrator. So let's take a look at my telescope. There it is. It's about 10 feet away on the other side of this wall. So let's go ahead and open the cover. And then we'll go ahead and look at our first target. So I chose, in terms of targets, we're going to at least do 1 star. And so by the way, guys, if you have any questions, now is the time, or like when we do the exposures, you can ask as many questions as you'd like, because we'll have a little bit of time. But we're going to start by looking at a pretty straightforward star, and that's Alpha Gemini, or Alpha Geminorum here. So let's go ahead and slew the telescope to it. All right. So I picked that star for a good reason. First of all, it's a relatively bright target. It's well placed in the night sky. And it is also a reference star. So there's a spectral database called the MILES database, and they provide reference spectra for a number of stars, and Alpha Gem is one of those. All right. So there we are. So now we can go ahead and plate solve. We should be pretty close. Actually, we are dead on target. How about that? So now the next step is we're going to use PhD2. So here you're looking at what the guide camera sees. And I might have to refocus ever so slightly. So just a sec. It's a little bit blurry. Maybe I'll go in the other direction. No, that looks worse. I focused it before the meeting started, but there you go. That looks a little bit better. All right, I think that'll do. So now let's center. So this is our target here, the bright star. What you're seeing here and here, they're just artifacts, they're reflections from the slit. So the slit has a certain thickness, and there's light that reflects on both sides of the slit. So that's why you're seeing those artifacts. So now let's go ahead and center it. That black line you're seeing in the middle is the image of the slit. All right. So in PhD2, you can do view spectrograph slit to display this little rectangle, and you can adjust its position. So now we can go ahead and start tracking. And using the second instance of Nina, we can do a first exposure. Let's do 10 seconds. All right. And so this is our spectrum. Okay, so the telescope is not well focused just yet. I probably want to. So I have to fiddle with this just a little bit and do a couple of test exposures. All right, that looks better. Yeah, that looks pretty good. Cool. So this is our spectrum. So it's a line. Obviously, the light is dispersed perpendicular to the slit. What you're seeing here, this little dip, I don't know if you can see it clearly, but I can zoom in. This is the H alpha line. Okay, so it shows up in absorption. So let's do this. Let's start a quick sequence. This one is going to be relatively short, and so this is the name. We can actually name it alpha gem, and we're going to do 3 exposures, or you know what? Let's just do 2 exposures of 60 seconds. And so I just want to show you how what I do here. So precisely centering the target onto the slit is something that I have to do manually. Okay, this is not something that I'm able to automate today. Some people have been able to automate it with some level of success using scripting in an application called Prism. It's an application that's made by a French company, but I don't use Prism, and I've been thinking about how I could possibly automate this. This is a pretty interesting problem to solve. But up until now, what I do is I manually center the target onto the slit, and then I start my sequence. And so the sequence, what it does is it takes ROI exposures. So it uses, I have a plugin. I use a plugin called, I think it's called the Lucky Imaging plugin. Yeah. And it gives you, in Nina, it gives you a new container which allows you to take ROI exposures of arbitrary parts of your image. So what we are doing here is just two exposures of 60 seconds. And then the system is going to stop guiding, close the panel cover, turn the light on, do one ROI exposure with the neon bulbs on, and then turn the light off and then open the cover. So let's see what happens. This is the first image. It is going to come through here. There you go. So now you can see the H-alpha line pretty well. I just turned off the automatic stretching. And then we can also look at what happens here. So, sometimes I do 10 exposures of 15 minutes each. So I just start the sequence, do some stuff around the house, and all of this happens automatically. There is one instruction at the very end. Oops, sorry. There is one instruction at the very end that's pretty important. And it is an external script to stop tracking, because otherwise the mount would continue tracking the sky and potentially hit a limit, which is something I want to avoid. By the way, it's not possible to do a meridian flip. All right, so now the cover should close automatically. There you go. And then the lights are automatically turned on. And then there's a new exposure that started. And so the exposure here on the neon bulbs is just going to show like a barcode. We're going to see 5 relatively bright lines, emission lines, and those are have a very well-known wavelength. And the software we'll use to process those images is able to detect those lines and recognize them, and so it's able to do the calibration all by itself. So let's wait for the exposure to complete. If you guys have any questions, please feel free to unmute your microphone and ask them now.
I think I must have missed it, but how many cameras and what is each camera doing?
Yeah, it's 3 cameras.
Okay.
So hang on, I'll go back to my slide in just a sec. Okay, so now we can see the barcode that comes from the neon bulbs. So if I go back to my slide real quick, specifically this one. All right, so you understand there's one camera here that's attached to the finder scope. So this is just to do plate solving. And the reason I have to do this is because the field of view on the guide camera is too small, or the usable field of view is too small, and plate solving often fails. This is the guide camera. So that's what we connect to in PhD2. And this is the science camera. This is where we acquire the spectra. Make sense?
So there's like a split mirror or something?
Yeah,
there?
the slit itself is a mirror.
Okay.
Yeah, and so it reflects the light towards the guide camera. There's a secondary mirror as well here. But yes, that's how it works. Make sense?
Right. And you have to align the guide scope with the telescope very accurately then, or?
Sort of accurately. This is something that I did a few nights ago, so I don't have to do it tonight. And it remains very, actually what I noticed that I just attached the finder scope to my telescope and it was already aligned because I had aligned it before. So, but yes, you have to align it. Doesn't have to be super accurate, but within a few arc minutes.
Okay, thank you.
Any other questions?
The bottom line is you need to get it within the field of view with your guide scope, or or I mean, not the guide scope, with your the one.
Correct. So if we go back to what my phanoscope sees, right? So this is our target, and this is what you see in PhD2. So as long as when the camera attached to the phanoscope is able to plate solve and places the target in the middle of the frame, it should be roughly in the center of the field of view here. Okay.
And then
That's
you move it around with the guide camera.
And then I move it around first using the mount controls, and then I lock onto a start guiding, and then I can do some adjustments. So I'm going to show you again because we're going to do another target. So this one, I just wanted to show you really quickly the procedure. So I picked another target, one that's a little bit more interesting because, I mean, the spectrum of I can show you what the spectrum looks like, the one that we just captured. And it looks like this. There you go. Okay, so that's the spectrum we just captured, processed and calibrated. I did it right before the meeting started. So I picked another target, which is relatively interesting. It is a B star. Okay, and so you're probably wondering, wait, what is a BE star? The BE star is a star of spectral type B, so a very hot star. But sometimes it has its H-alpha line in emission, right? I mean, if you look at most stars, and if you look at H-alpha, you're going to see an absorption line, like I just showed you, right? If we look at this spectrum again, most stars will have the H-alpha line in absorption because the outer layer of the star will absorb the light in that wavelength. But some B stars have sometimes their H-alpha line in emission, and that's because there's a cloud or a disk of hydrogen around that star, and there's dust and other material, and that is excited by the super high emission from that star, and then glows in H-alpha. Okay, so we're going to look at one of those. So B stars are pretty interesting, and they're the topic of a lot of research. And here, what I'm showing you is a website called BESS. So that's a database. And amateur astronomers and professionals can submit their spectra, and I do it regularly. So the star we're going to look at tonight is BN Gem. There you go. And so we can look at spectra that have been acquired by other amateur astronomers of the same star. So for example, there's an astronomer of the name DuPont who used a 16-inch telescope and a StarX spectrograph, and he obtained this spectrum. And you can see that the H-alpha line is in emission. Okay, so let's try and see what we get on this target. So in Carte du Ciel, I have installed the necessary catalog so that it's able to recognize this designation here. Let's glue the telescope to it. So again, feel free to ask any questions at this time.
All right, so the spectrum that you just showed either was two different emission spectras with a hole in between, or else it was one wide emission spectra with a HA notch in it.
Okay, so you're talking about this here, right? So this is actually a really
Yes.
interesting. Yeah, this is a really interesting question. Maybe we can tackle this a little bit later in the presentation, or while I'm doing an exposure. Okay. So let me get back to this in just a minute. All right. So I've centered our new target here, and there it is. It's right here. So what I can do is I can click on a star, start guiding. Actually, you know what? No, it's a little too far. So I can first roughly center it using using the mount control. Okay. And when we're pretty close, I can click on a star, start guiding, and then you have something called adjust log position in PhD2. I think it's in the tools. Yeah, adjust log position. And this allows you to precisely center the target onto the slit. Okay. All right, so I think now we can probably good enough. All right, maybe we can try to do a quick exposure here. This is a dimmer star. Let's see what we get.
So what would happen if it's not perfectly centered? Would the spectra be too dim because you're not
yeah, or you won't see anything.
Okay.
All right, so this is our spectrum. So it's pretty dim. So we can go ahead and do a new restart the sequence here. And then we'll do slightly longer exposure. We'll do 3 of them. That will give us 6 minutes, so I can answer questions during that time. All right, there you go.
And how sensitive are your results to atmospheric conditions, weather, that sort of thing?
Yeah, I'll answer this question first, and then I'll remember to go back to the other gentleman's question. So, I mean, the atmosphere is something that we have to take into account. Professionals do too. It is possible to correct for it to some extent. And the software I'm going to use to process the spectra, called SpecINT, is able to do this. So there's multiple corrections that you have to apply. One that we'll cover in just a little bit. I don't want any spoiler, spoiler at this time.
Okay.
And but there's also like the removal of telluric lines, which is possible using the software.
Interesting.
So the atmosphere is something that we have to take into account. Now, the thing is, when you submit a spectrum to a professional database like the BEST database that I just showed you guys, you don't correct you correct only for some things. You correct for your specific instrument, but you don't, for example, they ask you specifically to not remove the telluric lines. And there's a reason for that. They actually use those lines to validate that your spectrum is correctly calibrated.
Okay. And then ambient light is also not, you can correct for that as well. So like whatever stray.
Yeah. So in high resolution, it's not a huge deal. In low resolution, it is a big deal. So you will see the spectrum of the light pollution. Okay. You will see also the spectrum. Like, there are natural lines that will appear. Like, for example, the ionized oxygen lines will show up And those are either from sky glow or in some cases even from auroras. You can actually see those very easily in San Jose. And so, but the biggest problem for me, at least, is the continuum light pollution that comes from LED lights.
Right.
That can be somewhat. I mean, the software that I use to process my spectra is able to subtract that from the spectrum. So it's kind of like DBE in PixInsight, but you are left with the noise. And that's a big problem when you're going after faint targets.
Okay. Thank you.
So the other gentleman asked, why do we have this kind of weird profile? So B stars have interesting, let me see if I can blow this up, have interesting profiles that change over time. So some stars, I should probably show you guys, there's another website called, I didn't have it open, but I wanted to show you why I picked those targets. So B stars, some of them require they require a lot of observations because they evolve very fast. So if we look for our star, B and Gem, okay, you see it's green. They ask for one spectrum every year because that one doesn't change that much. However, some other stars can change very rapidly, and so they ask for one spectrum every day. Okay? So on some stars, you'll see the spectrum will look like this one day, and the next day it will look different. So why does it look exactly like this? It's because the cloud that surrounds that star, in this case, is a disk, and it just so happened to be aligned with our line of sight. And that's what creates these two peaks. The peak on the left is the part of the disk that turns towards us. Okay, so it's Doppler shifted towards the blue. And the peak on the right is Doppler shifted towards the red. And you have a trough in the middle. So that's because, again, it's a disk that's aligned with our line of sight. If it's not aligned with our line of sight, the profile will look different. There are, if you're interested, there is a good Wikipedia page on B stars, which explains, there are also a lot of books that explain why you're seeing the spectrum that you're seeing. Okay, so in this case, it's not super obvious. By the way, this is what's called a 2D spectrum. What you're looking at here is called a 2D spectrum. And the goal of processing is to turn a 2D spectrum into a spectral profile, which this is a spectral profile, okay? And you'll see that the processing, spectral processing is surprisingly similar to processing in astrophotography. A lot of the same concepts apply. All right, so we're almost done here. Any other question?
Are you doing a region of interest on the sensor? Because this is a square sensor, right? Like we're not seeing the squares.
Correct. So here you can see, I don't know if you can see my pointer very well. You can see this is the region of interest I picked, and I have to pick the same one every time because my darks and biases were done on the same exact region of interest. So I didn't choose these numbers randomly, okay? But I mean, like everything else is black in the image. So that's why it makes sense to use an ROI in this case, because you only really care about the central portion.
Well, why don't you reduce the height? Do you need that, like most of it is still black, right?
Yeah, good question. You do need the background sky because the software is going to use, basically the software is going to identify where in the image the spectral line is. And so it's going to assume that the rest is background sky. it's going to compute some mean values and then do some subtraction. Okay, so this is our neon lines. So now that we are done with our target, we can go ahead and process it. There is one more step I need to do, and then we'll go ahead and quickly process this image. All right, so B and gem. So I'm going to copy this to all right, so one thing that's a little bit annoying about this software is that I need to, it has very strong conventions, and so it expects all the files to be named in a very specific manner. Otherwise, it does not work. All right, perfect. So now that we have this, let me introduce you to this software. So this is called SpecInt. There's a UI called SpecInt Editor. And this is both the best and the worst software I've ever seen. So it's the worst software I've ever seen because it's not user-friendly at all. In order to use it, you're going to have to read pages and pages of documentation. A lot of errors are not well handled. Sometimes it will fail for no good reason or for no obvious reason. When you're a beginner, it's kind of difficult to get into it. So although it has gotten better with this new version, but it's also really good software because once you get the hang of it, you can process an entire night of spectroscopy in just a few minutes. And so processing really has been commoditized. So anyway, so it's kind of an interesting piece of software. All right, let's select our directory here. And then, oh, you know what? What time is it? 8:17. All right, we'll limit ourselves to only one target because I don't want this presentation to run too long. So we took 3 images. Okay, so I'm going to go ahead and start the processing. Hopefully it'll work. All right, perfect. So there is our spectrum. Okay. Now, the exposure, I only took 3 exposures and they were 2 minutes long, so you get a lot of noise. If I were to do this properly, I would have taken much longer exposures and more of them, of course. But you still see the same profile that we saw earlier. Now, I have a question for you guys. This is a BE star, so a star of spectral type B. And as you can see here, the spectrum goes up towards the right. The right here is the red, the left is the blue. And I mean, if you remember what the Planck profile looks like, for a B star in around H alpha, it should be going down, not up. So does anyone have any idea why that is?
Is it the silicon spectral sensitivity?
Say again?
Is it the silicon spectral sensitivity, which tends to peak at 800 nanometers?
You're onto something, but let me explain. So when you do spectral processing, what this thing did, by the way, I should explain which images it used. So I fed it these 3 images, which have the actual spectra that we captured, the neon reference. I also gave it dark, a master dark, a master flat, and a master bias. Okay. And with that, it's able to create a calibrated spectral profile. That being said, we need to do additional corrections. My spectrograph and my telescope, it's not perfect. It doesn't have a perfect efficiency across the entire spectrum. So in order to correct this, I calculated what's called the instrumental response. And explaining how I did that is a little bit beyond the scope of this presentation. But I had it commented out, and now I'm going to uncomment it. And we're going to process the same spectrum again. And then we're going to see the impact that makes on the final spectrum. So you can see it does, this is interesting. I should probably bring it up. All right, so now that looks a lot better. That looks like what you would expect, right? It goes down when you go towards the red. And again, we have the same interesting profile that I talked about earlier. Cool. All right, so next, it's 8:21. Maybe we have time for one more. I also have no, you know what? I have a bonus object. Let's go directly to the bonus object. All right, so the bonus object is Jupiter. So we're going to look at the spectrum of Jupiter. So before we do that, I just want to point something out. You see these emission lines that come from the neon bulbs? They're pretty vertical, right? They're ever so slightly, there's what's called a smile. If I was not taking an ROI, it would become very clear that they're actually arc circles. The software actually does some correction for the smile. You can see here smile correction. It's also able to do slant correction. So the spectrum is not always perfectly horizontal. These lines are not always perfectly vertical. It's able to correct for all of those geometric irregularities. So it's a pretty advanced piece of software.
What causes those slants and curves?
Oh boy, this is beyond my pay grade. It, like, to understand that would require very good understanding of the optics of the spectrograph, and I've never really taken the time to.
Okay, so it's the, in short, it's the result of the optics. I didn't think that it was the result of the emission of the neon.
No, not at all. It is the optics, yeah. All right, so now we have Jupiter here. And let's see if we can center it roughly. All right, cool. Doesn't have to be perfect since it's such a big target. And let's do a 10-second exposure. It's probably enough. So again, these lines are roughly vertical, right? Okay. You know what? I'm going to do a longer exposure. Let's do 30 seconds. So we'll see things a little bit better. 25 seconds.
So it's not saturating because of the slit?
I'm sorry, say again?
You know, with a normal astrophotography setup, you couldn't take a 10-second exposure of Jupiter. It would be all saturated.
Oh, right. No, I mean, like it disperses across the entire spectrum, so that's why you have to take relatively long exposures. So, by the way, like the dimmest object I can reasonably reach with this setup in high resolution is about magnitude 11. Okay, with my low resolution spectrograph, I can go to about magnitude 15. All right, so here's the spectrum of Jupiter. Let's zoom in a little bit and see what we see. So
You
first,
tell us what lines you would expect to come off of Jupiter in terms of nanometers?
yeah, so what kind of lines would I expect to see off of Jupiter? I would expect to see the solar spectrum, right? Because the light that Jupiter emits is actually sunlight that's reflected by Jupiter. And what we're seeing here is the H alpha line in absorption. This is actually the solar spectrum. However, do you notice that the lines are at an angle? Right? Whereas the neon lines I was showing you earlier are vertical. So
And also they're wider. They're much wider than I would expect.
Yeah, but who can tell me why they're slanted?
The rotation?
Yes, exactly. So that's due to the rotation of Jupiter. And the reason we're seeing the slant is because the slit is aligned with the RA axis, roughly. Right? If the slit had been vertical, you wouldn't see, those lines wouldn't be slanted. We would see other interesting things, but you wouldn't see those slanted lines. Okay? So that's Jupiter. That was the bonus object I wanted to show you guys. All right, so let's recap. We looked at the spectrum of a reference star, Alpha Gem. We captured and we processed the spectrum of a B star, BN Gem, and then we looked at the spectrum of Jupiter. Cool. So now I have a few more things I want to talk about. So let me quickly park my scope. And I will also close the cover.
Why is it that you can't do a meridian flip?
That's a good question. So if you do a meridian flip, I mean, think about it. When you do astrophotography in NINA, right? When you do a meridian flip, after the meridian flip, NINA is going to recenter the object. Mm-hmm. Okay. And I explained earlier that in order to center the object, it's a manual step. It's something that I would have to do myself. Right? So, I mean, you could technically do a meridian flip, and then I would have to go and manually recenter the object. Also, it would have to be exactly in the same position. It's just usually what I do is I stick to only one side of the meridian and stop when the object.
So it's not a mechanical thing or an optical thing. It's just because the meridian flip routine that NINA does has all the other stuff in it you don't want.
Well, I mean, the meridian flip that NINA would not be able to. I would not be able to. Oh, there you go. This is the bug that I want to report to the NINA maintainers. That instance just died, and I think it's caused by the RTSP player. No big deal. All right. Where was I going? Oh yeah, so the meridian flip, like NINA would not be able to do any plate solving. Mm-hmm. I used two instances of NINA.
Yep.
Right? One for plate solving, and then one for acquisition, and then I used PHG2 to precisely center the target onto the slit.
Yep.
So this is not something that software can handle well today. Maybe in the future it could be, but that's just not the case today. So
it's the meridian flip automation that's the problem, not that the setup can't do a meridian flip in terms of the mechanics or the optics of the system.
Right.
Yeah. Okay.
Okay. Let's go back to the slideshow here. So I wanted to talk a little bit about why I think amateur spectroscopy is so amazing. when you look at a star, when you take a photo of a star, all you see is a dot. If you're like, it can be brighter or dimmer, it can have some color, but you can't really tell much from that. With spectroscopy, you can actually study those objects. So we looked at BE stars, and those are fascinating objects. I invite you to read more about them on your own time. But I wanted to outline also talk about some of the other type of objects that amateurs have been studying using the same spectrograph that we've been using tonight. So cataclysmic variables like recurrent novae is something that is being studied carefully by a lot of amateur astronomers. Remember, amateur astronomers have a superpower, and that is the fact that there's many of them, and they have a lot of time. They have a lot of telescope time, whereas professionals don't have a lot of telescope time. And some of those objects are actually quite bright. You're not going to reserve time on the VLT to study a magnitude 8 star, right? That doesn't make any sense, especially if you need to study it almost every night. So amateur astronomers actually have a huge role to play in spectroscopy. So François Tessier is the administrator or the person behind the ARIS database and the ARIS forum. Is a bit of a specialist in cataclysmic variables in the astronomy community and has worked with professional astronomers like Steve Shore and has done a lot of remarkable work in that area. Extragalactic supernovae also are really interesting. Robin Leadbeater from the UK is someone who's done a lot to categorize supernovae as soon as they're announced. Sometimes he's able to point his telescope, and before professionals, he's able to say, oh, it's a supernova of this type or of that type, using a very simple spectrograph. So there's a lot of interesting work to do there. I've done a low-resolution spectrum of a magnitude 15 extragalactic supernova with a smaller telescope than the one you just saw. So it's pretty cool. Spectroscopic binaries. That is also a fascinating topic. And I've actually participated in a study that resulted in the publishing of a paper, which you can see here. I think you can, yeah, there it is. I'm here. This was part of, this was a StarOS campaign. So I'll talk about StarOS in just a little bit. But this paper is fascinating because with a lot of observations, they were able to do some amazing things. First, they were able to get an amazing accuracy of 0.014 angstrom. I'll say it again, 0.014 angstrom. Right, so my spectrograph, the one we used tonight, has a spectral resolution of 0.3 angstrom. So that's 0.03 nanometers. Okay, so if you think your 3 nanometer narrowband filter has a narrow band, not really. Like the spectrograph is able to do 100 times, has a resolution of 100 times smaller than the bandwidth of a narrowband filter. But by collecting a lot of different data from a lot of different people, they were able to reduce the resolution down to 0.014 angstrom, which is just unbelievable. In terms of Doppler shift or Doppler velocity, I think that comes down to something like 500 meters per second or something like that. So I think it's enough to detect Doppler shift for some of the bigger planets orbiting or other stars. And then they also did some really interesting math using Python to disentangle the spectra of the two companion stars. So again, it's a spectroscopic binary. There's two stars orbiting each other, and with some clever math, they're able to disentangle the two spectra, which is just fascinating. And also one of the stars has an interesting profile. You can see here, there's a little break. I forgot exactly what this is caused by, but there's a lot that can be learned from the spectrum of a star. All right, let's go back to this. Asteroids and comets composition. So this is something that some amateur astronomers also study very carefully. Specifically comets. There's a lot of things that can be learned from the spectra of comets. You can see the auroras on Jupiter. So I think I have it somewhere here. This is done by a very famous French amateur astronomer called Christian Bulle. He's the person behind who created the SOLEX and StarX project. And here he shows how he was able to detect the polar arc around Jupiter. So, which is just unbelievably fascinating that he was able to do this with a relatively simple telescope and kind of an old spectrograph already. So that's one thing that can be done. Io's sodium cloud. So Io is one of Jupiter's satellites, and it's a very active satellite. It has a lot of volcanoes, and there is a sodium cloud around Io. And so some amateur astronomers, like you can see here, have been able to detect the sodium cloud around Io. So this is all in French, but it's just another fascinating thing that people have done with very small telescopes, by the way. Here, I think Guillaume Bertrand was using a, 80 millimeter refractor, something like that, 72 millimeter refractor f6. So that shows you that with very, very humble telescope, you can just do amazing things. You can also detect Mercury's exosphere and look at its composition. So I think I have, so the detection of the doublet of the sodium doublet around Mercury. So this is also done by Christian Bulle. You can, with a small amateur telescope, you can uncover the existence of dark matter. So some amateur astronomers have looked at the spectrum of ciphered galaxies. So those are galaxies with active galactic nuclei. And they do different slices of the galaxy. And from that, they're able to draw a rotation curve, and they're able to demonstrate that it doesn't follow the Keplerian laws of motion, which means that something else is causing the stars to move faster than they should on the periphery of the galaxy. So again, this was done with a very small telescope. This is an 8-inch telescope. Okay. You can also image stellar surfaces using a technique called Doppler tomography. So again, think about it. You take the VLT, or you take Hubble or JWST, you point them at a star, all they're going to see is a dot. And yet, amateur astronomers equipped with their little telescope in their backyard and a 3D printed spectrograph are able to image the stellar surfaces and show that there are dots or spots on the surface of the star that are moving. So this uses a technique called stellar tomography. So stellar tomography is it's a little bit complicated to explain how it works, but it's the same exact system that's used in a CT scan. Okay, except that here we use it's the Doppler effect that causes lines to move around the spectrum, and then there's a lot of really complicated mathematical analysis that has to take place. But basically, from a series of spectra, it's technically possible. You can see how there's like features that move over time as the star rotates. And from that, it's possible to reconstruct what the star looks like. and it's also possible to figure out the angle of the rotation axis compared to our line of sight. So that is possible with. For this, you need a spectrograph with a very high resolution, higher than this one, probably about 50,000. This one, the one that we use tonight, is in its current configuration has a resolution of 20 to 25,000. So with a spectrograph that would be able to go about twice as far in terms of spectral resolution, this is technically possible. You can only do this on a small number of stars, those that rotate sufficiently fast and that have large spots. But there's a few of them in the sky, and some of them are relatively bright. So this is just something that completely blows my mind. With a slightly different version of the spectrograph, you can also image the sun. So this is what's called a spectroheliograph, right? So SOLEX, if I can quickly go to the SOLEX website. So SOLEX originally is a spectroheliograph. StarX is just an extension of SOLEX in order to use it for nighttime targets. And SOLEX is able to, I don't know if you guys saw the recent video by Dylan O'Donnell, where he showed a spectroheliograph, and that apparently stirred a lot of interest in the amateur astronomy community. So with a spectroheliograph, you're able to image the sun in many different wavelengths. So of course, you're able to look at it in H alpha. This is with a SOLEX and a small refractor. But you can also look at it in here, sodium and helium. And you can also do what's called a Dopplergram. It looks like this. You can also draw a map of the magnetic field of the sun. So that's called a magnetogram. And this uses an effect called the Zeeman effect, where the magnetic field can cause absorption lines or emission lines to double up. Okay. And there is software that was created by French amateur astronomers Christian Buil and Valérie Denou that's able to pick this up and effectively render an image of the magnetic field of the sun. On the left is the one that was created by an amateur astronomer using an 80mm refractor and a SOLEX, and on the right is a professional version, and you see that they match very well. Okay. Some amateur astronomers even have remotely operated semi-professional setup. So there's a team, again, another French team called Two Spot, and they set up a pretty large telescope. Actually, it's two telescopes now in Chile. And they have a pretty advanced spectrograph called an HL spectrograph, which gives you a very broad spectrum across. It allows you to look at the entire visible spectrum, for example, but with the same resolution as a high-resolution spectrograph. And it uses a fiber optics. Their setup is really complex, and they're able to control it remotely from Europe. And they do a lot of really amazing work. Every time there's an alert, they quickly jump on it and get some results. I can show you the photo of their equipment. It's pretty impressive. There it is. Two telescopes on a big 10 micron mount. And then finally, you can image the jets of a black hole. From your backyard in San Jose, you can image the jets of a black hole. And I'm not kidding about that. So this is something that I actually participated in a couple of years ago. So there was a program that was organized by that Staros Association, which I'll talk about in just a minute. And the idea was to image a target called SS433. So that's a summer target. It's kind of a dim, it's a magnitude 13 object. And there's a really good book about it, by the way, that you can pick up used on Amazon, The Quest for SS433. I highly recommend it. It's really interesting. But basically, this is a binary system. There is a black hole and a large star. I forgot what the spectral type is. And the black hole so there's an accretion disk, and then there's a jet. So what we did, there was a group of amateur astronomers in France, and I participated in it as well from here. We all banded together, and we took as many low-resolution spectra of SS433 and then sent it to one person who then put them together. And this is what we obtained. So it's a little bit difficult to parse, but basically what you're seeing here is the H-alpha line in emission. It's in emission because the accretion disk around the black hole emits a lot of that light. And then there's an interesting feature that you can see here, and that is also H-alpha line, but it is Doppler shifted at a different amount depending on the day. And that's because the jet of the black hole, the black hole itself, its axis of rotation spins due to the presence of the companion star. So it's like a precession phenomenon. And so this is what we see. And actually, if you look closely, there's even a second type of precession that you can see a little bit or kind of guess. And I'm not quite sure what causes it. I remember reading about it a little bit, but we were surprised to see this phenomenon as well. So effectively, we imaged the jet of a black hole using a spectrograph that's 3D printed. All right. I want to finish up by sharing a few references. If you think that spectroscopy is something that you would like to give a try, I highly encourage you to do a lot of reading. So you can start with the Solex and Starex website. So that would be this one. It is in French, but if you click in English, it's pretty much all of it has been translated now. And it will give you a pretty good overview of what this spectrograph is about. It explains how to build it if you want to build it yourself. And there's a lot of really interesting stuff here. Processing, stars. So Christian Buhl and Valérie Denou put a lot of work into this. All right, the next one is, oh yeah, there is a mailing list that you can join if you'd like. So this is the URL for it. And then there is the Staros project. So the Staros project is basically observing campaigns for amateur astronomers. And you can look at some of those campaigns that are still open, and the data is freely accessible by anyone. And some of those campaigns eventually result in papers being published. So this is a really cool project. It's been kind of quiet lately, but I hope that they'll restart and do more campaigns soon. It's a lot of fun. SunScan. So SunScan is an interesting project. This is for if you're interested in spectroheliography, or basically imaging the sun using a spectroheliograph. The SunScan is sort of the equivalent to the C-star, right? So the C-star, you just turn it on and it just does everything and works. The SunScan is basically the same concept. There's an iPhone app or an Android app, and then you can control this little device. You roughly point it towards the sun, and you can obtain some amazing images. You can also purchase this whole thing already made from Azure 3D Print. Cheliac Instruments is a company in France. They sell spectrographs that are fully assembled and ready to go. They're a little pricey, but these are turnkey instruments that you can just attach to your telescope and they'll work and you'll get support and so on. And they also sell optical kits for StarX and SolX. So this is a really good company. And they also sell books about spectroscopy. Azure 3D Print is it's a 3D printing company in France. They are specialized in doing equipment for amateur astronomy, not just spectroscopy, but they have that custom version of SolX and StarX, which I have. I highly recommend it. It's really, really good, and I have a review of their StarX Pro on my YouTube channel if you're interested. There's the RS Forum, a little bit more advanced, I would say, but lots of interesting discussions. And then I put Christian Bull's website and YouTube channel. Unfortunately, a lot of the videos are in French, but with YouTube's auto-translate feature, you can kind of get the gist of what he says. It's really fascinating. Cool. I think I'm done. So now if you have any questions, I'll stop sharing my screen. And I'm happy to answer or try to answer any questions you might have.
For the solar, I'm going to say it wrong, with the helioscope?
Spectroheliograph.
Heliograph, thank you. Has anybody done like false color, because you have all the different wavelengths? Have they treated it like a deep space target and made color images from it?
Yeah, some people have. I mean, remember, these are scientific instruments. The goal is not to obtain like
make pretty pictures.
Yeah, the goal is definitely. I mean, you saw the images that we captured tonight. They're kind of ugly looking, but they're beautiful from a scientific perspective. But some people have done that. What you suggest, yes, for fun.
Okay, thanks.
Did you say the diffraction grating was 2,500 lines per millimeter?
Yeah, so the one that we're using tonight is 2,400 lines per millimeter.
How do they make that? That's my interest.
Yeah, so hang on. The other two gratings that I have, one that I use for low resolution in the visible spectrum and the other one low resolution in the near infrared spectrum, they are 300 lines per millimeter. So how do they make those? They're sort of the same principles as those used to make computer chips. So I don't know the exact process, to be honest, but I know that it is a process of, what is it called? Lithography or something like that. Same process to make computer chips.
Okay, thank you.
Yeah.
Hey, Julien, you showed some pictures of like the sun and stuff. And what I don't get is, I mean, as I understood it, you were taking a single point and measuring its, frequency composition of the light coming from that single point, not the whole.
Yeah, so that's a good question.
Grid.
So yeah,
How
so
do
when
you
you
do
use when you use a spectroheliograph, you basically scan the entire surface. So what you do is you record a movie of the spectrum. So you have again an ROI, say around H alpha, and you're going to record a movie of that. And then you're going to feed that movie into a piece of software that then reconstructs the image of the sun in that wavelength, which is kind of mind-blowing when you think about it.
And the movie needs to be taken with the array tracking off, right? So that it scans in front of the slit.
Actually, the way most people do it is they scan using their mount at a specific speed. Yeah, and so I've never done it myself, so I'm not definitely not the expert, but they do run at like 4x or 8x signal speed, and then they have like a 1 millisecond or 2 millisecond exposure. Yeah.
So a full picture would take a while.
Well, no, it doesn't take that long. It takes maybe like 30 seconds or a minute. to capture
so
the
it
movie,
scans
and then
pretty
you have,
quickly because
yeah,
you're
and then you
taking very short exposures because the sun is so bright.
yeah, and then you have the time to scan the entire solar surface at 4x the sidereal speed. Will take something like 30 seconds, and then you take that movie, you give it to a piece of software like JSOLX or Inti, and it will spit out the image of
Oh,
the
you
sun.
don't have to go back and do a second line and a third line and a
No,
100th
no, no,
line.
no. I mean, but you'll get the image of the sun in a very specific wavelength. Then, if you want, you can go and rotate. You see that this little thing here, you can rotate it, point it to a different part of the spectrum, say sodium, and then you can scan again the sun.
But the way you're saying it, you're implying that you get a whole line of exposure for each, millisecond exposure. You get a whole line of image. But I thought you'd only get a single pixel, not a line,
No,
because
no,
you're
no,
taking that line and you're moving it,
no,
anyway.
no. You're no, no. It's you get the image of the slit effectively.
Oh, and the frequencies are orthogonal to that?
Yes.
Oh, okay. So you get a whole line. So that
Yes,
when
you
you
get a whole
scan.
line, and then as you scan, the software is able to reconstruct the image. Yeah.
Oh, okay. Thank you.
What we saw tonight, that one horizontal line, is effectively the image of the slit. Right. The reason the rest of the thing is black is because there was nothing else in the slit except that one star. But all you see really is just the image of the slit spread across all the wavelengths. Yeah.
Oh, okay. Thank you. All right. Are there more questions?
How many people are, after this presentation, how many people here are interested in giving spectroscopy a try?
I have tried it in the past with just a grating and RSpec. That's as far as I went with it.
That's a good way to, honestly, that's a good way to start. It's relatively inexpensive. It's relatively easy. You just pop it into your filter wheel. That being said, I didn't start with that. I went straight to a StarX because I knew I wanted to eventually, give it a real try. And StarX is just infinitely more powerful than a basic transmission grading.
Yeah, I'm kind of interested in the solar stuff. That's a little bit more visual than just looking at the the spectra. Yeah.
Yeah.
So why are so many French people interested in spectroscopy?
That's actually a really good question. I have no idea, but I think it's just I think it might just have started from a couple of individuals who were just crazy about that, and it just snowballed from there. But yeah, I don't know. Good question.
So is there any benefit from getting, more, not more resolution? What's the opposite? More range and with high resolution, like, I don't know, recapturing at
Yeah, I mean,
different
if
point?
if you go to Lake Observatory, I encourage all of you, if you have never been to Lake Observatory, I encourage you to go. And if you go on a public night, you can even talk a little bit to the astronomers, ask them what kind of spectrograph they use. Like, professional astronomers, they rarely take pictures. Let me put it to you this way: JWST rarely takes pictures. When you see pictures of JWST, they're really done just for the public consumption. But once they did the pretty pictures to justify the big budgets that are necessary to make those programs possible, then the science comes in, and then all they do is spectra, pretty much. That's all they do. So if you go to Lake, you can ask them what kind of spectrograph they use, and they'll explain that they all use A-shell spectrographs because those are, by now the best they give you like the best trade-off. You can see a large part of the spectrum, but you also have the high resolution at the same time.
Yeah, and they're $1 million spectrographs and such, and they're the size of a refrigerator, right?
And well, yeah, and so that's the thing is StarX is interesting because it's attached to the telescope, right? But if you want to have a high enough resolution, inevitably, because of physics, the spectrograph has to be a certain size. And so it's no longer possible to just carry it on the telescope. So what we do instead is we put the spectrograph in a climate-controlled room, and we have fiber optics that goes from the telescope to the spectrograph. So that solves some problems. That also creates other problems, which are also very interesting to solve. But I think that's what they do. Also, although at Lake they have what's called the Nasmyth configuration, where the light always reaches the same point. So maybe they don't have a fiber optic system. But they do a lot of infrared spectroscopy at Lake, or near infrared spectroscopy. And so they use some really interesting calibration bulbs in order to calibrate their spectra. But by the way, everything I showed you tonight, the professional astronomers have to do the same thing, right? So the instrumental response, the darks, the flats, the reference spectra, all of those things, professional astronomers have to do the same thing. There's no difference. Even JWST has to take into account its own instrumental response. So these things are just common across the board.
Though they may not have to recalibrate constantly, or do you think they do? I mean,
I don't have to recalibrate constantly.
okay.
I mean, I don't like the instrumental response is stable over time. I don't have to recreate it. However, when I take the spectrum, I always take the spectrum of a reference light immediately before or immediately after, because when the spectrograph is attached to the telescope, depending on its orientation, there will be flexure in the housing of the spectrograph that may cause some very slight shift and of like just a few pixels, but that's enough to ruin your calibration. So that's one thing that you have to take into account as well.
So how do you know that your calibration is ruined? Because the spectra makes no sense, or
you can actually look at, you can use the Tillery clients for that. So I didn't talk too much about that, but the atmosphere is there, and there are absorption lines that are very much caused by the atmosphere. Also, when you do long exposure spectra, you will see natural emission lines show up. So you can verify your calibration using those as well.
okay, makes sense.
All right. Well, maybe at this point we should call it a night. Thank you so much, wherever you are. Marcel, do me a favor and mute so we can see Julien again. Hold on, I'll do that. There you go. Maybe you needed to talk. Okay. Well, everybody, please unmute now and give Julien a big hand. That was a wonderful presentation.
Thank you, Julien.
Thanks, Julien. It's amazing.
Thanks. Yeah.
Thanks, Julien.
Thank you.
All right. Well, thank you. And we'll see everybody next month. And until then, clear skies.
See you next time.
Bye.
Bye now.